All right, so let's start. So last time we started, let me just remind you what we have done. So we were discussing circle. Okay. Okay. Right. So the shape to define this, we first define so-called covariant derivative. What was it? Well, we have a surface in R3, and we have a vector field on R3. Well, defined on R3. Sorry, on M. And whenever we have a vector for any V in TPM, we define the covariant derivative of the vector field along the vector V as the derivative of z of alpha t, where alpha is a curve defined on some interval, let's say, containing 0, so that alpha 0 is equal to p and alpha prime 0 is equal to p. So this is nothing but the directional derivative of actually z along the vector v. Here we may consider z as a function from R3 into R3, right? Defined on M. We may think it this way. And we have this lemma. If z has the, so let the vector field z is given like this. Here zi's are functions, differential functions. Then this covariant derivative is nothing but, so the directional derivative of z along v is nothing but the following. So r from 1 to 3 is r sorry, z r and ui's are, of course, are just this vector vectors or vector fields. 1, 0, 0, constant vector fields. 0, 1, 0. At any point, it is the constant vector field. We may actually consider this way. one P just is P. Or, of course, this is just D on the function Zi times U. Same. Okay, then we define so-called oriented surface in this situation. A surface and R3 is called orientable. If there is a continuous function from R3 so that U of P is U, U of P has perpendicular here from in other words, so if you have tangent vectors like this, okay, UP is perpendicular to all of them. So it's something like this. And it's perpendicular to all these vectors. So it is perpendicular to the tangent space. All right. Now here comes the object which will take, which will be the main study of surfaces, so-called shape operator. If P is enough, is a point, then for each tangent vector, SG, which is defined as this object, covariant derivative of Q. U is a unit normal vector field that unit normal vector field and defined so this object is defined like this. Okay. This SP is called the shape operator. So what it does, this is just derivative of normal vector field, unit normal vector field along this vector. So you measure how this normal vector changes as you move along the vector B, right? Suppose this is your surface. Okay. Suppose this is your surface, and you are at this point. Here are two vectors. One vector is like this. Let's say this is one. Another vector E2. And what you do, so what is SP1? It is the derivative of E1. So you along the vector E1. What is U here? U is a unit normal vector field. For example, it can be this vector field. So it is this. It will be, normal surface. Vector normal. On this curve, my vector field U looks like this, right? This is, let's say, of course, here, so I just draw the vectors on this curve, but of course, all over the surface, I have vector field. Okay, not just this. For example, on this curve, this is a saddle surface, right? Saddle surface. You know this from calculus, advanced calculus, right? When you study local minimum, maximum, this is a saddle point, right? It's a local it's a critical point where you have no maximum or minimum. So, for example, on this curve, the vector field looks like this, which is everything wrong. Let me show you that. Aşağı gideceğim. Yani aslında bize de bakması lazım. Okay, so this. And this expression measures how this vectors changes as you move along the vector V. Okay. So let me write down this explanation. Note that the shape operator SP along the vector V measures how fast the normal vector, unit normal vector Q yazdım sadece. Changes as we move. From the point P'den ayrıldığımızda nasıl değişiyor? For example, you know, if you consider this cylinder, okay, now suppose this is the point P, so our normal vector is like this. And suppose I want to measure how the vector field changes as I move along this vector. So as you move along this vector, does the normal field changes? No, right? So for this one, shape operator at P along the vector P, which is just the covariant derivative of U along P, but it's 0, right, for this vector because it doesn't change, right? Of course, if you choose some other direction, right? Suppose you move along this curve, which is a circle, right? So if you let your vector to this guy, let's say this is P1, P2. So this P2 measures how the normal vector changes along this curve at this point, right? Here, of course, it will change, right? It is pointing upward at this point, but as you move along the circle, it will just bend, it will be horizontal at this point, and then it will point downward at this point, and so on. So this won't be 0 probably, and we will compute this in a minute. Sorusu olan var mı? So this is the shape operator. Why it is called shape operator? Well, it tells us how the surface changes, and it does it by measuring how its normal vector field changes. Okay, so it tells us how the object actually looks like. That's why it's called shape operator. If, for example, shape operator is 0 at all points, what would you think? It should be a plane, right? Normal vector doesn't change at all, right? Normal vector doesn't change at all, so it's flat, must be flat, therefore it must be plane. Of course, that needs a proof, but you know that's the basic. Okay, now the computations with this shape operator, we need some facts. First of all, for each point in M, the surface in R3, the shape operator is a linear operator. That's why it's called shape operator. I mean, operator. This is an operator in the linear algebra sense. Shape is a linear operator. Okay, now let's see why this is the case. From the definition, it is not clear, right? It is not clear why it's an operator, because Operator means it should take a vector from a vector space and it should send it to some other vector in the same vector space. So we need to prove this. SP takes vectors from this vector space, tangent space, and it should send them to the same vector space. And it is not clear, why this gadget should lie inside the tangent space. Okay, so we will see that. Linear, it is not just a linear transformation, it's a linear operator, meaning that it takes vectors from the tangent space at the point P and sends them to the tangent space at the same point. Okay, now, since it is a unit vector field,
Hocam kamera ortada kaldı.
we have right length of UP square, which is just UP dot UP.
Hocam.
One that comes. So this constant function must be 0.
Hocam.
Okay. Kimse de beni uyarmadı. Okay, let me
Hocam.
evet.
Az önce söyledik de sanırım sesimiz gelmedi size.
Çünkü kulaklık olmadığı için bende.
Hı, anladım.
Okay. All right, so let me describe you what we had done last time. We will do shape operator. For that, we define so-called covariant derivative of a vector field along a vector. We did this last time, and then we showed how actually one can compute covariant derivative, right? Covariant derivative. Once it is given in a frame, it is computed as follows. You basically just take derivatives of the coefficient functions along the vector v. So it is equal to this gadget. All right. And last time again we defined so-called orientable surfaces. A surface is orientable if we have a continuous vector field which is normal to the surface at all points. Okay, in other words, you have a vector field UP so that UP is perpendicular to the tangent space TPM at all points. And then today we defined shape operator. If you have a surface M at any point, the shape operator at the point P along the vector V is defined to be the vector, which is just the covariant derivative of a unit normal vector U along a vector along the vector V. So the value of the shape operator at the point P for any point for any vector at that point is defined this way. Okay. So at each point, this is an operator, meaning that it will send a point at the point tangent to the surface at the point P to another vector tangent to the surface at the point P. Okay, and here we made a simple observation that, you know, if you look at this cylinder and consider the unit normal vector which I drawn on this curve, you see that it is just constant, right? As you move along the cylinder on this top curve, it is constant. Therefore, the shape operator along this vector v1, which, you know, goes in this direction at the point P, must be 0 because the vector field u doesn't change, right? Doesn't change. But if you go along this circle, then of course the normal vector field will change. Therefore, it won't be probably 0. And we have this lemma which says that shape operator is really an operator, meaning that it takes vectors tangent to the surface at the point P, two vectors tangent to the surface at the point P. And to prove this, we observe that since U is a unit normal vector field, right, like this, so at each point I have a unit vector, right? This is my normal vector field. The length of each vector is 1. Therefore, this gadget is 0. Right? Because this is the constant function 1, its derivative 0. But what is this? From the properties of covariant derivative, this is just what? How would you take the derivative of a function? This, well, here this function is the dot product of two vector fields. This is nothing but the covariant derivative of the first one along the vector v, dot product with the second one, plus u dot the covariant derivative of the second vector field along the vector v. But dot metric, so this is just times this gadget, meaning that this dot product is 0. Hence, whatever this vector is, it must be perpendicular to u. But what is u? U is our normal vector field, so this is perpendicular to u, meaning that this gadget, okay, lies in the tangent space, right? Since it is perpendicular to the normal field, it must be tangent to the surface. So we are done. It takes a vector in the tangent space and sends it to another vector in the same tangent space. Well, we must also check linearity, because we say that it's a linear operator. We showed that it takes values in TPM, but we must see why it is linear. Well, we just do this for any real numbers a, b, and vectors in TPM. What is this? Well, this is just minus the covariant derivative of u along this vector, But we've seen last time that when I have something like this, this is basically just the dot product of gradient of the coefficient of u with the gradient of this with this vector. Therefore, it will just decompose, and you will have just minus a times del v u plus minus b times del omega u. And what is this? This is just a times the shape operator along v, and b times shape operator along u, along w. Değil mi? Bunu geçen hafta yapmıştık. So this finishes the proof. Here's a remark. The map U, which sends points of M to the sphere S2, right? Unit normal vector. Unit normal vector can be regarded as a point on the unit sphere, right? Because the vector in R3 of length 1, therefore it's a point on the sphere. So unit normal vector field can be regarded as a function from the surface to the sphere. And it is called, the Gauss map. Okay. So normal vector field can be regarded as a function between two surfaces. But this surface is something very special. It is the unit sphere in R3. It is defined by Gauss. Ya da dur, şu tahtayı sileyim ondan sonra. Burada zamanım var mı? Var. Okay. All right. Let's continue a little bit. So I regard it as a function from surface to the sphere, which takes yeah, and its derivative will be what? At any point, TPM if you are at this point on the surface, you have this normal vector, let's say. So this is our normal vector. That normal vector can be considered as a point on this sphere, right? This is S2. So this point is just UP actually, UP. And if you draw the tangent spaces to the surface and to the sphere, they will be the same planes, right? What is the tangent space to the surface at this point? It is the plane which is perpendicular to this vector, right? Şunu tabii. Okay, so it is tangent space here will be, let's say, something like this, and here will be something like this. But both tangent spaces, so TPM and T, what is this point? UPM, UPS2, right? They are planes in R3 which are perpendicular to the same vector. Therefore, we may regard them as the same planes, okay? So T, UP, S2, right? It takes a vector here and sends into what? U star V. This is nothing but minus, so this is minus the shape operator. If I regard this as a function from the surface to the sphere, the tangent map at the point P along the vector V will be what? It will be just the derivative of this function along this vector, and it is minus the shape operator. So Gauss map can be considered as the tangent map of this function, okay? Here, of course, we identify these two tangent spaces, okay? Why is that? But because they are planes in R3 which are perpendicular to the same vector, okay? Therefore, I can regard them as the same. Note that both TPM and TUP S2 are planes in R3 having the same normal vector, right? The normal vector here is UP, the normal vector here is UP. And thus, we may regard them as the same. That's why, you know, this becomes a function from TPM to TPM, because this tangent spaces can be regarded the same. Okay. So the shape operator is just minus the derivative of the Gauss map. Okay. Here's an example. So let's sigma be the sphere of radius r. A sphere of radius r. Then the outer normal field, normal vector field to sigma is given by UP, which is just 1 over r times xi ui. Where these xi's are, of course, the coordinates of, sorry, yeah, coordinates of the point P. So the normal vector at the point P is nothing but the vector, right? I regard this just as a vector, and as a vector, it is equal to this gadget. For the sphere, for a sphere of radius, let's say r, right? The normal vector at any point, let's say at this point. So this is the point P. What is the normal vector? It is this vector. This has length r. This should have length 1. Therefore, I divide it by r. The coordinates of this point are just x1, x2, x3. But that coordinates are just actually coordinates of this vector joining origin to the point P. And this normal vector is just 1 over r times this vector. Therefore, UP is just 1 over r times ui times xi, where xi's are the coordinates of the point P. Okay. All right. So hence, for any vector, we the covariant derivative of u along v will be what? Here r is just a constant. I am taking, okay. Right. How would you compute the covariant derivative? According to the lemma, which I told you at the beginning of the class, and we actually studied it last time, derivative of this object will be what? These are just constant vector fields, so I'll just take them out. we will just take derivative of this functions, coefficient functions along the vector v, and this is again a constant, so it will goes out from 1 to 3, and then derivative of x along the vector v, but that is just v of xi times ui. Okay, so what is the shape operator then? So this will be just this is minus of this, therefore it is minus 1 over r times I from 1 to 3 v of xi times ui. Here I should write p actually, because you know, this is happening at the point p. So yeah, this v is a vector at the point v, right? At the point p. Okay. But what is this? So let's say if v is the vector, let's say v1, v2, v3, then what is v of xi? I just take derivatives of this, right, along the directions x1, x2, x3, and multiply them by this vector, components of this vector. So this is nothing but derivative of xi along x1, v1, so this will be what? This will be just they will be 0 or 1, right? If I is equal to one of these, it will be 1, otherwise it will be 0. So this is just v1, right? Because these are either, this is Kronecker delta I1, this is Kronecker delta I2, this is Kronecker delta I3. So this is vi. So what is this gadget then? Okay, minus 1 over r. This is just vi times uip. But what is this summation? These are the unit vectors, right? 1, 0, 0, 0, 1, 0, and 0, 0, 1. I multiply them by this constant, the coefficient, the components of the vector, and then add them up. Well, this is just the vector v itself. So the shape operator for the sphere of radius r is just the identity operator times 1 over r. So let me just write that down here. Hence, the shape operator V is just minus 1 over R times the identity. So it is V, just the identity operator V times V, right? Where so for the unit sphere, the shape operator is just minus identity. For a sphere of radius R, it is just minus identity times 1 over R. Okay. All right, let's stop now.